Hello dear students, this is Vishal sir from Ikra High School. Today we are going to study chapter 10 Gravitational from standard 9 NCERT syllabus. Let's first read the lesson. In chapters 8 and 9 we have learned about the motion of object and force as the cause of motion. We have learned that a force is needed to change the speed or direction of the motion of an object. We always observe that an object dropped from a height fall towards the earth. We know that all the planets go around the sun. The moon goes around the earth. In all these cases, there must be some forces acting on the object, the planets and on the moon. Isaac Newton could grasp the same force is responsible for all this. This force is called the gravitational force. So dear students, today we are going to study about gravitation. It is an invisible force that we have already talked or we have already felt in our life. We know that the force of earth binds us to the earth. It keeps every object on the earth. Even the atmosphere is bound to earth because of gravitation. So does that mean that only earth has a force like gravitation? No. The moon also has its own gravitation. Even the sun has its gravitation, which keeps all the planets in their proper position. So one more question arises. Does only the planets have their gravitation? Absolutely not. All objects which has mass, that means a matter, has its own gravitation. It pulls every other object towards it. Then why isn't every other object pulled towards all the objects? Because the gravitation force depends on mass. Let's read further to understand it better. Gravitation. We know that moon goes around the earth. An object when thrown upward reaches a certain height and then falls downward. It is said that when Newton was sitting under the tree, an apple fell on him. The fall of the apple made Newton start thinking. He thought that if earth can attract an apple, can it not attract the moon? Is the force same in both cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of its orbit, the moon falls towards the earth instead of going in a straight line. So it must be attracted by the earth. But we do not really see the moon falling towards the earth. So in that section also, you got the question. Why does only earth attract every other object? Why doesn't the other objects attract earth towards it? Let's try to find out through an experiment. In activity 10.1, we have tied a stone at the end of a string and the other end of the string is holded by us. Now move the string with the stone in a circular direction. Release the thread. Note down the direction of the motion of the stone. You will find that before the thread is released, the stone moves in a circular path with a certain speed and changes direction at every point. As you can see in the diagram, the dotted parts are the point that the stone changes its position. At every point, the stone changes its position. The change in direction involves change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along a circular path is acting towards the center. That means the force that keeps on moving the stone in a circular path is towards the other end of the string, that is your hand. Your hand has the force to keep the stone in a circular motion. When you release the string, it will go in a certain perpendicular direction. Now, the force that is at the center of the circular path is called the centripetal force or the force that seeks center. So, every object or every matter on earth or in the universe has its own centripetal force and that centripetal force generates gravitational force. Now, the point from where the stone will move along when you release it is called tangent. If you see in the diagram over here, in the section more to know, you will find 3 points, point A, B and C. The point B is the point from where the stone will be released. As soon as the stone is released, it may move in the direction of A or C, but it will be perpendicular from the center. This shows the tangent of a circle. The motion of the moon around the earth is due to this centripetal force. The centripetal force is provided by the force of attraction of the earth. If there were no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards the apple. Why? According to the third law of motion, the apple does attract the earth. But according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. That means the earth and the apple both attract each other. But because the mass of the earth is huge compared to that the mass of the apple, earth will attract the apple rather than apple will attract the earth. So we do not see the earth moving towards the apple. The same argument is said for earth does not move towards the moon. In our solar system, all the planets go around the sun. So we can say for that also there exists a force between the sun and the planet. But the fact that we have concluded shows that not only the sun attracts the planet also attracts the sun towards it. And because of this, every object remains at their position. The earth has a constant distance from the sun, like all other planets have their constant distance. Due to the gravitational pull on each other, they do not move towards each other, they remain at their position. And this force of attraction is called gravitational force. This could be understood better by a mathematical representation of that force. Universal law of gravitation. According to it, every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. The force is along the line joining the center of the two objects. Here you can see two objects, object A and B, with different mass. Object A has greater mass while object B has less mass compared to A. And the distance between both the mass from their center is d. It is not from the edges of both the objects. The distance is measured from the center of the objects. So, from both the centers, the distance is considered as d. Let two objects A and B of mass m and m, small m, lie at a distance d from each other as shown in figure 10.2. Let the force of attraction between the two objects be F. According to the universal law of gravitation, the force between two objects is directly proportional to the product of their mass. So, the force that they both are going to generate is in direct proportion with the product of their masses. And the force between the two objects is inversely proportional to the square of the distance between them. That means, if the distance between both the objects is increased, the force will decrease. While if the distance is decreased, the force will increase. That gives you force is in indirect proportion to the square of the distance between them. Let's take the example of the two objects given A and B. Let two objects A and B of mass m and m lie at the distance d from each other as shown in figure 10.2. Let the force of attraction between the two objects be F. According to the universal law of gravitation, the force between the two objects is directly proportional to the product of their mass. That is, force is in direct proportion to the product of the masses of the objects. And the force between the two objects is inversely proportional to the square of the distance between them. Let's consider it as d. So, the force that you will get, or the force that both the objects apply on each other, will be in inverse proportion to the square of the distance between them. Now let's combine both the equations to form a singular equation. Force varies to m into m upon d square, which will give us force is equal to g, where g is the universal constant which was calculated by Henry Cavendish, into m upon d square. Now let's cross multiply. So F into d square is equal to g m into m. Then you have to substitute m into m on other hand side, which will get us g is equal to f d square upon m into m. That means if you need to find the gravitational force between any two objects, you can apply this formula. The constant of g was calculated by Henry Cavendish. The value of g was accepted as 6.673 into 10 raised to minus 11 Newton meter square per kilogram square. So this brings us to a conclusion that there exists a force of attraction between any two objects. The objects may be on the earth or in the universe. Now let's study the importance of universal law of gravitation. The universal law of gravitation successfully explained several phenomena which were believed to be unconnected. The first phenomenon that it explained was the force that binds us to the earth. Why don't we fall from the earth? So that was explained by the universal law of gravitation. The second phenomenon was the motion of the moon around the earth. The third, the motion of planet around the sun. So these two phenomena, the motion of heavenly objects around different heavenly objects, was also explained by the universal law of gravitation. The fourth phenomenon was the tides due to the moon and the sun. So the tides that happen twice a day on earth in the oceans was due to the gravitation pull of the moon and the sun. That was properly explained by the universal law of gravitation. Free fall. Let us try to understand the meaning of free fall by performing this activity. Take a stone, throw it upwards. It reaches a certain height and then it starts falling down. We have learned that the earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the earth under this force alone, we say that the objects are in a free fall. Is there any change in the velocity of falling object? While falling, there is no change in the direction of the motion of the object. But due to the earth's attraction, there will be a change in the magnitude of the velocity. Any change in velocity involves acceleration. Whenever an object falls towards the earth, an acceleration is involved. This acceleration is due to the earth's gravitational force. Therefore, this acceleration is called acceleration due to the gravitational force of the earth. It is denoted by small g. The unit of g is same as that of acceleration, that is meter per second square. So in this part, children, we understand the gravitational pull that the earth makes also increases the velocity as the object comes towards the earth. Just take for an example, if you leave some object in air at some height, it will definitely fall with the velocity. Though you have not given any force, it has the change in the velocity at every point the distance. This shows the change in velocity, which is considered as acceleration. And this acceleration is due to the gravity, the pull of the earth. The earth pulls every object down, and while it pulls, it increases its velocity, which results in acceleration. That is why that acceleration is called g, small g, as the acceleration due to gravity. The unit is also similar to acceleration, that is meter per second square. We know from the second law of motion that force is the product of mass and acceleration. Let the mass of the stone in activity 10.2 be m. We already know that there is acceleration involved in falling object due to the gravitational force and is denoted by g. Therefore, the magnitude of the gravitational force F will be equal to the product of mass and acceleration due to gravitational force. That is, force is equal to mass into acceleration due to gravity. F is equal to mg. From equation 10.4 and 10.6, we have mg, that is force is equal to g m into m upon d square. Or you can evaluate the equation and write g is equal to g m upon d square, where m is the mass of the earth and d is the distance between the object and the earth. Here, the distance between the earth and the object should be measured from the center of the earth. If you are standing on the earth, that does not mean the distance between you and the earth is 0. It is the radius of the earth. Let an object be on or near the surface of the earth. The distance d in equation 10.7 will be equal to r, that is the radius of the earth. Thus, for the object on or near the surface of the earth, mg is equal to g m into m upon r square. which will be reduced to G is equal to capital G, that is gravitational constant, into the ratio of mass of the earth and the radius of the earth in square. The earth is not a perfect sphere. As the radius of the earth increases from the poles to the equator, the value of G becomes greater at the poles than at the equator. For most of the calculation, we can take G to be more or less constant on or near the earth. But for object far from the earth, the acceleration due to gravitational force of the earth is given by equation 10.7. To calculate the value of G, we need to put all the values of the gravitational constant, the mass of the earth and the radius of the earth, which are G is equal to 6.7 into 10 raised to minus Newton meter square per kilogram square. Mass of the earth is 6 into 10 raised to 24 kilogram and radius of the earth is 6.4 into 10 raised to 6 meter. So, putting all the values and evaluating, you will get approximate value, that is 9.8 meter per second square. Thus, the value of acceleration due to gravity of the earth, G, is equal to 9.8 meter per second square. Now let's study what happens to the object that are under the influence of gravitational force of the earth. Let us do an activity, activity 10.3. Take a sheet of paper and a stone. Drop them simultaneously from the first floor of a building. Observe whether both of them reach the ground simultaneously. We see that paper reaches the ground little later than the stone. This happens because of air resistance. The air offers the resistance due to friction on the motion of the falling object. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do that experiment in a glass jar from which air has been sucked out, that means the vacuum part, the paper and the stone would fall at the same rate. We know that an object experiences acceleration due to free fall. From equation 10.9, this acceleration experienced by object is independent of its mass. This means that all objects, hollow or solid, big or small, should fall at the same rate. According to a story, Galileo dropped two different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. As G is constant near the earth, all the equation for the uniformly accelerated motion of the object becomes valid with acceleration A replaced by G. The equation will be V is equal to U plus AT, S is equal to UT plus half AT square and V square is equal to U square plus 2AS, where U and V are the initial and the final velocity and S is the distance covered in time t. In applying these equations, we take acceleration A to be positive when it is in the direction of the velocity, that is in the direction of the motion. The acceleration A will be taken as negative when it opposes the object, when it opposes the motion. This clearly states that when the object is falling towards the earth, it is having a positive direction, while it is going away from the earth, it is having negative direction. Thank you.